Okay, this video is about trigonometric substitution, and this is for integrals that look like an arcsecant, but they're not an arcsecant, and they're not a u-sub. So this is our arcsecant. Notice it's got an x squared minus a squared under the radical. You've got an x out front. You've got a constant in the numerator. If the integral looks exactly like this, or maybe there's a constant, we can factor out the constant. You can use this rule. It's just a basic rule, and it's one that we derived back in Calc 1. So now we're in Calc 2, and you see an integral that looks like this. Man, that's tempting. It looks like an arcsecant. Almost. There's not an x here. Now don't think this is an arcsine. A lot of students confuse this with an arcsine, but remember your arcsine rule looks like this. Arcsine has the a squared minus x squared. So you've got the constant squared minus your variable squared. That's arcsine of x over a. If I've got an x squared minus a squared, and there's no x out front, it looks like an arcsecant. It's almost identical to an arcsecant, but the missing x means it's not an arcsecant. So we're going to do something. We're going to do a secant substitution, because it has an x squared minus a squared in it. We're going to let x equal a secant of theta, and the procedure is very similar to the procedures that we followed with the tangent substitution and the sine substitution. This is a little bit different. There's one tiny difference because of the nature of the domain and range of tangent and secant, and there are lots of things. I'm going to put that in a different video. In this video, I'm just going to tell you what to do, how to do it, how to do a secant substitution, and I'll make a separate video about why the restrictions are what they are for those people that want to know. Okay, so if it looks like x squared minus a squared, and it's not an arcsecant, and it's not a u-sub, and of course it's not a basic rule, then we're going to do a secant substitution. Notice I've got an x squared minus a squared, and there's no x in the numerator. If there was an x up here, I could do a u-sub, but there's no x. There's no x down here, so it's not an arcsecant. So we're going to do this. So we're going to do what we always do. First, prepare to substitute. And this is where it gets a little funny, but I'll show you. So first we say, identify a. A squared is 100. So that means a is the square root of 100, which is 10. And then if a equals 10, we're going to let x equal 10 times secant of theta. Then you want to compute dx, so we got to substitute the dx in terms of theta. And we want to simplify square root of x squared minus a squared, or just x squared minus a squared in general if there's no square root in your problem. So I've got x equals 10 secant of theta. Derivative of 10 secant of theta is 10 times secant of theta times tangent of theta. Don't forget your d theta. And this radical expression can be rewritten in terms of theta as well. You're just substituting. You're just replacing x with 10 secant of theta. And don't forget, if you've got a times b squared, you've got to square the a, square the b, square all the factors separately. So I'm going to square the 10, I'm going to square the secant. Factor out the 100. You see it? You see it coming? Yes, it's exciting. Secant squared minus 1 is tangent squared. Very nice. Now this is where it gets a little different. The square root of 100 is of course 10. And we might be tempted to say that the square root of tangent squared is just tangent. And that's true most of the time. Well, part of the time. The square root of x squared, I know we take advantage of this rule all the time. We want to say it's x, don't we? We want to say that no matter what we put in, if I square something and then I take the square root, I get x back. But that's not 100% true. This is almost always true, or that's true about half the time. This is true as long as x is positive. These guys undo each other under those circumstances. If you don't believe me, plug in 2. What's 2 squared? 4. What's the square root of 4? 2. So these guys just undo each other and you just get the 2, which is what you expected, right? What happens if we put in negative 2? Negative 2 times negative 2 is positive 4. The square root of positive 4 is 2. So I can't just cancel the square root and the squaring function on this one. If I took a negative and I squared it and then I took the square root, I get the same number back but positive. So it turns out that this is not always equal to this. It's only equal to this when x is positive or 0. In general, that's equal to that. Now we didn't use that rule whenever we did our sine substitution or our tangent substitution because it really doesn't affect the answer in those cases. But because of like differences in the SIGN sign of the secant function and the tangent function, and the differences in domain and range with the arcsecant and arctangent functions, like all of those things, those come into play. So when I take the square root of tangent squared this time, I'm not going to call it just tangent of theta. I'm going to call it the absolute value of tangent of theta. And if I'm on an interval where x is greater than a, we're going to say that the square root of x squared minus a squared is a times the positive tangent of theta. And if I'm on an interval where x is less than negative a, we're going to say that x squared minus a squared is the negative a times tangent of theta. Now, I know it seems like an arbitrary rule. You're like, why are we doing that? That's for another video. And to figure out which bounds I'm going to use, am I going to use the positive one or the negative one, I have to look at the bounds of the original integral. Now, this time we got lucky. There were no bounds. If there are no bounds, you can just assume it's positive tangent of theta, and your answer might be off by a sign. If you take the derivative, you'll still get this function back. Everything will work out just fine. But technically, we should have the absolute value of tangent of theta right here. So we're just going to say this equals tangent of theta, because we don't actually have any bounds for x. I don't know if x is greater than 10 or less than negative 10. So I'm just going to assume that tangent of theta is positive. So I'm just going to say for tan theta greater than 0. Keep that in mind and add that restriction to my answer. Mathematicians do that stuff all the time. They just add a little, well, I can keep going if I assume this is positive, and then they just keep going. That's what we're going to do. Okay, so we've prepared to substitute. We're going to replace x with this. We're going to replace dx with this. We're going to replace this square root with this guy, knowing that sometimes that's not legal for this secant substitution. And now we're going to write our integral in terms of theta. So we're going to substitute. You're going to simplify. And then you're going to anti-differentiate in terms of theta. And everything should be very nice. So I had 1 over this square root, and just dx. That square root, we just did all of that work. That square root is equal to 10 tangent of theta whenever tangent's positive. And dx, well, that's 5 secant theta tangent of theta. All right, why did I say 5? Did I say 5? I think I did. 10 secant theta tangent theta d theta. So that goes right there. Replaced my dx, I've replaced my square root. Now we're going to simplify and anti-differentiate, hoping we've got a rule. And this time we're pretty lucky. The 10s reduce, the tangents reduce. And of course I've got a rule for secant of theta. It's one of those you might have forgotten. It's natural log of the absolute value of secant of theta plus tangent of theta plus c. Now at this point I want this final answer in terms of x, not secant and tangent. Secant and tangent, or theta was just some variable that we made up in order to be able to anti-differentiate this. I didn't know the antiderivative of this, but I sure do know the antiderivative of secant of theta. So this substitution made it possible for me to get rid of that integral and get to the answer. Now I got to get back to x somehow. And the way we tend to get back to x after we prepare to substitute and simplify is we draw a triangle. And we label the sides using the original substitution. Okay, so draw my right triangle, boom. Always like to put my theta over there. And I remember my original substitution was x equals 10 secant of theta. So if I get secant of theta by itself, by dividing both sides by 10, I get x over 10 is equal to secant of theta. That's giving me 2 of my 3 sides of the triangle. Now you might not remember what secant of theta is in terms of adjacent, opposite, and hypotenuse. But remember, you can always go back to SOHCAHTOA. Ah yes, that triangular mountain. Or this camp t-shirt. It says Camp SOHCAHTOA on it. I remember those days at Camp SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Secant is 1 over cosine. So it's not adjacent over hypotenuse, it's hypotenuse over adjacent. So we're going to flip that. Make that hypotenuse over adjacent. So hypotenuse is x, adjacent side is 10. And then this time I'm not going to derive it. If we use the Pythagorean theorem and solve for this side, we're going to get the square root of x squared minus 100. We get that square root that was in the original problem, that guy right over there. It's always how it happens. It's always how it works. Okay, so we drew this triangle. For what purpose? Remember, the purpose of drawing this triangle is to write our final answer, which is here, entirely in terms of x, not theta. Because theta was just something we made up so we could take the antiderivative. Now I'm trying to get back to x, so I'm going to back substitute. My answer is natural log of something plus something else plus c. And first is secant. Well, I already know secant is x over 10. So I'm going to plug that in. And tangent, that's the other one I need to know. From SOHCAHTOA is opposite over adjacent. Side opposite theta is that square root. The side next to theta is just 10. So we get this right here. And that is good enough for me, guys. That's our final answer. Now you might be one of those students who looks up the answer in the back of the book and you say, it's wrong. I got all of this and mine had these 10s in the denominators and their answer did not have a 10 in the denominator. And I would say, okay, you're still absolutely correct, you might say. How can that be correct if it's different? It's not different. It's just written in a different form. Okay, so we're done. We're done with Calculus 2. We're done with that part. We've gotten here. But we say, that's not what the book said. That's not what Chegg said. That's not what Wolfram Alpha said or some other software that you're using. This is what they did. First of all, notice that they both have 10s in the denominator, so I can write that as a single fraction. Add the numerators and keep the common denominator. Okay. You guys good to go? You see it? It's okay if you don't see it. Back in college algebra, or pre-calc 1, or whatever they call it at your institution, you probably learned this rule. Remember, natural log of a quotient is natural log of the numerator minus natural log of the denominator? That's exactly what they did here. I've got natural log of this quotient is natural log of the numerator minus natural log of the denominator. Absolute value of 10 is just 10, of course. This is just a different constant. If this is C, I'm just going to call it C1. So if you look in the back of the book, and their answer is this, they're right. They might not have a 1 there. Their C is just different from your C. Your answer is equivalent to theirs, though. They just simplified that natural log of 10, and you didn't. And that's totally fine. And they're equivalent answers, and they're using this log property. It actually comes up quite often in other classes. We use log properties and exponent properties and differential equations quite a bit in order to solve for y after we have solved some differential equation. It's just something that you have to be familiar with. So you might want to keep that in your toolbox for when it comes up. But you are done right here. That's the right answer. Okay, so that's a secant substitution. Let's do one more secant substitution. And then we will call it a night on the secant substitutions. All right. This time I'm going to do one with bounds. Okay. Let's say I want the integral of the square root of x squared minus 4 over x, and I want to integrate from -5 to -2. Now this is not going to be a pretty answer because this is just a problem that I made up, but with this answer we're going to be able to practice choosing the right form of the square root of a squared minus x squared. Okay, so we're here. Notice, first, I do not have a basic rule for that. You cannot take the square root of that part and that part. It's not legal. Don't do it. There's a minus sign there or a plus there. You've got to do that first and then take this square root. So it's not going to work. All right, so this is where we're at. Basic rules don't work. What about u sub? A lot of students are going to say, yes, u sub, because the derivative of x squared minus 4 is 2x dx, and I've got an x dx right there. No, you don't. Do you see why that's not an x dx? That x is in the denominator. It's not in the numerator. If that was x times that square root, sure, we could do a u sub and we'd be good to go, but that's a 1 over x as a factor. That x in the denominator isn't going to work for the 2x dx. So u sub fails. So it's not a basic rule. It's not a u sub. It's not integration by parts. It's not trigonometric integrals because there are no trig functions in it, but it does look like x squared minus a squared. And x squared minus a squared reminds me of that x squared minus a squared arcsecant antiderivative. So we're going to make our arcsecant substitution, or our secant substitution, excuse me. I keep wanting to write arcsecant, it's just secant. Now let x equal a secant of theta. Okay, so a squared is 4. So that means a is the square root of 4, which is 2. And if a is 2, then x equals 2 secant of theta. And dx is 2 secant of theta, tangent of theta, d theta. All right, so we're ready to substitute that denominator and substitute that dx. But I also need to simplify that square root. So we're going to replace the x with whatever it was in terms of theta. That was 2 secant of theta. And we've got a product here. A product squared, so I want to square the first factor, square the second factor. Factor out the 4. And secant squared minus 1 is still tangent squared, yay! But it's going to be positive tangent. Sometimes it's going to be negative tangent the other time. In general, we're going to get 2 times the absolute value of tangent of theta. Question is absolute value of tangent of theta equal to tangent of theta, or is it equal to negative tangent of theta on the interval that we were given? Well, remember what our guidelines said. Our guidelines said this is going to be equal to 2 tan theta when x is greater than a, so when x is greater than 2, and it's going to be negative 2 tan theta when x is less than negative 2. So which one is it for this problem? And how do you know? We have to look at the bounds. Now the bounds for this tell us where x starts and where x stops. Remember when we do area under the curve? Got some function. I don't know what it looks like, but I have some function. This says start at -5, end at -2. And I want that area. Of course, this is not that function. This function is 0 at -2. But you get the idea. It says start here and end here. So what this is telling me is find the area under the curve, or the area between the curve and the x-axis, the net area, when x is in between -5 and -2. That's my lower bound, that's my upper bound. So which one is it? Is x less than -2? It just should be greater than or equal to and less than or equal to. Or is it this one? Well, clearly from my picture, x is less than -2. So I'm in this case. So that's the one that we're going to use. So our first step was to prepare to substitute. And we've prepared. Now let's substitute. So we've got the square root in the numerator. This right here turns out to be negative tangent of theta. The denominator, that x, is 2 secant of theta. And dx is 2 secant theta, tangent theta, d theta. The 2's reduce, the secants reduce. End up with a -2 times the antiderivative of tangent squared. Now you might say that's not equal, Miss Townsend, and you'd be absolutely right. Do you see what I did wrong? What's the problem? That's not equal to that. This one has bounds. That one represents an area or a net area. Might represent something else. But that's a number. I'm supposed to get a number back from this. This is going to give me a function of theta. It's not going to give me a number. If I want to get the same number, if I want this to be equal to this, I need new bounds. You might say, Miss Townsend, I don't remember how to get the bounds. It's okay. I'll remind you. The way we get the bounds is we replace x with -2 and -5. We substitute that in over here. And then we solve for theta, because we need bounds for theta. These are bounds for x. This says start x here and end x here. When I have an integral in terms of theta, I need to know where theta starts and where theta stops. To find out where theta starts and theta stops, I need to replace those bounds in for x in this equation and solve for theta. Okay, so I need new bounds. So that's one thing I need to do to prepare to substitute that I didn't have to do on the other problems. It's okay. So we had x equals 2 secant of theta, and my upper bound was x equals -2. So when x is -2, I've got -2 equals 2 secant of theta. Divide both sides by 2. And you get secant of theta equals -1. Or take reciprocals. Reciprocal of -1 is -1. Reciprocal of secant of theta is cosine. You might say, when is the cosine of theta equal to -1? The cosine of theta is equal to -1 a lot of times, right? It's equal to -1 right there at pi, and right there at 3 pi, and right there at 5 pi. That equation has a lot of solutions. We're just going to take this first one, theta equal pi. So this was our old upper bound. So this is our new upper bound. Plug that in right there. Other one's a little bit harder. I don't think we're going to get an angle. I'm just going to get the arcsecant of something. That's okay. It's not a known ratio. Not one of those special angles that we studied back in trig. When x is -5, we're going to have -5 equals 2 secant of theta. So -5 over 2 equals secant of theta. So cosine of theta equals -2 over 5. So theta is going to be, running out of space on this paper, theta is the inverse cosine, or the arc cosine, of -2 over 5. So that's what we're going to do for our lower bound. I'm going to use that notation that I don't really care for because it just makes it smaller. Cosine to the -1, it's not 1 over cosine. It's the inverse cosine. But that's an angle. We could figure out what quadrants it's in. We could use our calculator to find it in radians. But it's just an angle, it's just a number. We're going to substitute that in over here. So I've got the inverse cosine of -2/5 here and pi over here. Now I've substituted. This integral is equal to this integral, which is equal to this integral. Now I want to take the antiderivative. I don't have a rule for tangent, but I do have one for secant squared. And tangent is the same as secant squared minus 1. So we're going to substitute. And then simplify. Now this is a little different. Anti-differentiate with respect to theta. Antiderivative of secant squared is tangent. Antiderivative of 1 with respect to theta is theta. You're going to substitute in inverse cosine of -2 over 5 and pi, and you're going to subtract, and that's going to be the answer. You do not have to back substitute. If you wanted to, you could evaluate the indefinite integral. You could find the antiderivative first and then plug in the bounds. Either way, you're going to get the same answer. So let's see what answer we get this way. Okay. So plug in that upper limit. Substitute in the lower limit and subtract. Subtracting a negative is adding. I've got tangent of the arc cosine of negative 2 over 5 minus the arc cosine of negative 2 over 5. Just an angle. And let's see if we can simplify it from here. That's our answer. Let's just not simplify it. It's tangent of pi. You guys remember tangent of pi? Well, tan pi is sine of pi over cosine of pi. Remember sine of pi? Sine of pi is 0. So this is 0. And cosine of pi is negative 1. So that's 0. So I have 0, and then I've got a 2 pi there. So that's that part. And then this part. Oops, I couldn't see what I was writing. There we go. This part I think I can leave alone. It's fine. It's not a special angle. But this tangent of the arc cosine of negative 2 over 5, that's something that we could find. Let's figure out what that is. So in order to do that, we want to remember arc cosine is going to give me some angle. I'm just going to call it alpha. So alpha is defined to be the arc cosine of negative 2 over 5. And remember, arc cosine always gives you an angle between 0 and pi. It's probably been a while since you studied that. It's okay if you've forgotten. Most of us have, except us math teachers. We review it a lot. Alpha is between 0 and pi. So if alpha is in quadrant 1 or quadrant 2, and my cosine is negative, cosine's negative, remember, when x is negative. So I'm going to be over here. Let me back up a little bit. Alpha equals this. And this means that alpha is the angle whose cosine is negative 2 over 5. So this is equivalent to the idea, or the fact, that cosine of alpha is negative 2 over 5, and alpha is between 0 and pi. That's what I've said here. I'm just trying to figure out what the tangent of alpha would be, because that's what I've got right here. Well, if cosine of alpha is negative 2 over 5, that means I go, I'm going to be over here, where x is negative. Maybe my hypotenuse is 5. That's alpha. Question is, what's the tangent of that angle? Well, to figure out what the tangent of that angle is, I just need the third side of the triangle. Let's call that y. Y squared plus negative 2 squared equals 5 squared. By the Pythagorean theorem, this squared plus this squared equals that squared. And subtract the 4 from both sides, and we get y squared is 21. So y is the square root of 21. Not pretty. That's okay. And now I can just look at this triangle to find the tangent of alpha. So the tangent of alpha, which is the tangent of the arc cosine of negative 2 over 5, is, according to right triangle trig, opposite over adjacent, so SOHCAHTOA. Opposite side is square root of 21. Adjacent is negative 2 when we expand right triangle trig to go beyond quadrant 1. All right, so that is that part right there. So I've got 2 times square root of 21 over negative 2 minus this arc cosine function, which is an angle. We could find it in our calculator if we wanted to. If I distribute the 2, I get this. That's my answer. I know that was a little bit messy. There was a lot of trig at the end. But the calculus ended right here. It ended a few minutes ago. So let's start this problem over again and review. So first I notice that I've got bounds, which is a little different than the other problems. And I've got an x squared minus a squared in my integrand. So I'm going to make a secant substitution. I decide to make the secant substitution. I identify a squared is 4, find a, then let x equal a secant theta, find out what dx would have to be, and then simplify the square root of x squared minus a squared. Now this is always going to be a times the absolute value of tangent, but the absolute value of tangent may or may not be positive tangent. It's positive tangent when x is greater than or equal to a. It's negative tangent when x is less than or equal to a. So with that in mind, we substitute. So that's our second step, is we substitute, simplify, and anti-differentiate. And in this case, because it's a definite integral, we're just going to evaluate the integral. We substituted, we simplified again. We had to use a little trig identity so that we had a rule for that. We took our antiderivative using our rules. Plug in the upper limit, plug in the lower limit, and subtract by the fundamental theorem. That's our beautiful answer. Not so beautiful yet. Just not simplified. We did a little trig review, which is always good for us. It's like eating your vegetables. And we got right there. And that turns out to be this net area under the curve. And that's just an angle in radians. Unitless angle. It's a number. If we get our calculators out, we can get that number in radians and approximate the value of that integral. So that's it, folks. That's the end of trigonometric substitution, at least as far as applying the formulas is concerned.